Today we're going to kick off with Terry Lyons, who is at Oxford and Imperial College. Terry's been a very active member of the community for many, many years, particularly as the developer of rough path theory and signature methods, which he's going to speak about today. So it's a great pleasure to welcome Terry as the first speaker in this new joint seminar. Terry, the floor is yours.
Okay, well, thanks very, very much for the invitation. I'm excited to have this opportunity, and I think it's a great idea that the two organizations work together on these things. Right. So I want to tell you in a as non-technical way as I can manage a series of viewpoints and examples of success to motivate you to try and understand the sort of thing that we are trying to bring in. Everybody understands, I think, that human beings have an intrinsic notion of number. And the point is really that makes it intrinsic is that it's sort of independent of the context. There is a five transcending both of these pictures in different ways, but it means very different things. But the point is that we are, as human beings, remarkably capable of understanding how to analyze and work with numbers without the context. But I would suggest that actually the human is capable of dealing with other things than numbers, that we haven't invested as much overt energy into quantifying and understanding as we have with numbers. And probably the most important one is our ability to understand streams of events and order in events. We understand that you have to put your toothpaste on the toothbrush before you clean your teeth. And we have a very innate ability in this direction. And what I'm really talking about, as I come to realize over the years, is that we are now developing a mathematical perspective that allows one to think abstractly about these problems without actually getting involved in the context. That's more radical than it seems, because we'll come across a couple of generic abstract problems where there are potential abstract solutions, but which I raised one of them with one of my statistics friends of many years recently. And his immediate response was, well, the first thing you need to do is you need to understand the context. Now, I am a great believer in the fact that the context tells you more, but this story is about what you can do, in a sense, before you bring in the context. We're very grateful that our calculator adds up numbers without understanding or needing to know whether those numbers refer to money, cars, or ideas. Stream data is absolutely everywhere. It could be a string of characters drawn on the screen, like here, where you're translating them into Chinese writing at the top. Could be an order book in the financial market, a piece of speech. It could be a great many things, but also it can happen that you have not one, but collections of streams of data. For example, the lives of 500,000 people on Biobank. And there are many key questions that one might actually like to answer relating to this. I live quite closely now. I think the three I'm going to focus on. One is a simple machine learning one of trying to understand functions on sets of streams. But more interesting ones are if I give you a cohort of streams, for example, those lives in Biobank, and now I have another stream, for example, my life so far, then I might like to understand whether my life fits into that data set. And if it does, perhaps I'd like to describe what's going to happen next on the basis of what's happened to other people like me. And these are very abstract questions. And I'm interested in trying to understand them in an abstract way. And here you see is another sort of example. But I mean, the truth is that these stream data examples are just everywhere. So this is one we had to deal with when we were looking at nitrous oxide levels in London. And so they often need translation, right? It's often that the actual representation of the stream you use isn't necessarily the full-blown stream that you started with. Well, I haven't got much time today. I have more time than I thought because at one point I thought I had 25 minutes. But the point I'm going to try and explain rather quickly, but actually it's certainly an important point, is that once you're in a multimodal context, once your streams have more than one coordinate, time series don't really work very well. But time series are what almost everybody uses to represent data. And they pay a big price. The essential price is, I explained, I hope, relatively carefully in the abstract, and some of you may have seen it, is that if you think about an interval of time, then a time series gives you the value at one end and some value at the other end, but it really doesn't tell you the order between the channels, which is only an issue if there's more than one channel in between. It doesn't tell you whether you got there before the bus or the bus got there before you, but the outcome, the consequences are substantially different. What that means is in real, complex, high-frequency multimodal data, if you are going to adopt the classical approaches that really go back to Newton of summarizing a path by its chords or increments or a time series, you're going to be forced to sample this data at a very, very high frequency. Once you do that, you realize that if you want to capture order, unfortunately, the dimension of the space of functions you're going to have to look at scales quadratically if it's just pairs with the number of terms you had to sample. So you see, you have this asymptotic catastrophe of how you are going to describe and identify and find functions that discriminate in a rational way between things that happen in different order, whether I catch the bus or not. Rough path theory, which really came from stochastic analysis and the need to make calculus work on Brownian paths, actually broke with this tradition of looking at time series. Well, in a way it did. It still looked at intervals, but instead of looking at the value at one end of the interval and the value at the other end of the interval, it takes a more sophisticated view of what happens in between. It actually uses group elements rather, well, so does increments. They're in RD, but RD is abelian. It uses non-abelian group elements to describe what's going on in this multimodal stream over an interval. This allows one actually in the end to come from the top down rather than the bottom up. And it is no longer necessary or desirable to sample so frequently. And instead, there is a trade-off, and you can describe what's going on using various group elements. There's a lot of similarity with reservoir computing. The real, and it's more like physics. So the real way that one thinks about the path segment and how one should describe it is rather than giving its values, painting a picture of what it looks like, you look at how it feels, you let it interact with nonlinear systems, and you look at the responses of the systems. That's what reservoir computing does, but it typically uses a system that is a black box. The essential difference is that in rough path theory, at least at the beginning, when you're thinking about the mathematics rather than the scalability, you start with very specific white boxes. And in fact, what you really start with is this differential equation, which is a non-commutative exponential function. And it turns out with relatively deep mathematics that that gives a complete description of what is going on. it gives far too many terms. It's a mathematical object, just as a real number is a mathematical object with infinitely many terms. In fact, it's worse than that because the depth k things explode exponentially. But if you had enough energy, you could describe your entire path in terms of these coefficients, and it up to precisely it captures the order of the events in the different channels. Conveniently, it forgets everything else. It's a sort of nonlinear filter that forgets the parameterization of the data. And that's a very good thing, actually, to forget that, because you can always put it in by adding in time or something to the coordinate charts. But you don't want that explosion caused by reparameterization of your data. Data science learning functions hate symmetry. Why does it hate symmetry? Well, there's multiple possibilities of describing the same activity, and you have to learn they're all the same. So if you can factor out a symmetry, and reparameterization is an infinite dimensional symmetry, then you're in a very good place. You've removed a very big, nasty infinity. Unfortunately, streams are sufficiently complicated that they're still exponentially nasty after you've removed that piece. And so, in fact, you have to work quite hard to make things work. But I want to tell you now about how just this perception of having a feature set, which is these group elements, can actually really change the way we model and understand streamed multimodal data. And by now it's having quite significant effects. So I showed you on the beginning the Chinese handwriting. Um, but actually that happened at the very beginning and was motivation to me for doing anything at all in this space of applications, because the original thing was to solve some serious theoretical questions. But then with my student James, and with other people too, Sam Howison, we entered a competition for the detection of sepsis. It was a fairly major one, actually, PhysioNet 2019. And it was very tough because James was really determined to do a good job. But at that point, this is already our first go at these things. And he really worked very hard, but we hovered about halfway up and he became more and more frustrated. But the good thing about that is he eliminated all the odd problems we could have had with the classical methodology. And then we realized we had a bug in our code. And when we corrected that bug, which took about 15 minutes, we leapt to first place in this competition with 100 and something entries. And that was a good start. And since then, we've applied it to lots of other things. And we won that competition, or James won that competition, I should say. The Chinese handwriting is, I don't know if it still is, but certainly at one point was used by about 75 million people every day. And actually, the key point was that the signature allowed you to give a local feature set that gave you the context of what was going on in the neighborhood. And that seems to be key. This is a meeting about finance. And many of you will know that in 2022, Hans Buehler, who was then, of course, at JP Morgan, was named Quant of the Year for his work in deep hedging. You may also know that a key part of that was in generating large data sets that could be used for the training. And the signature was a way of encoding and validating the way that the generative models worked so as to achieve the accuracy that's wanted. And it's quite well described in his prize citation. More recently, one finds many fairly simple examples where people have relatively complicated but not very complicated streams, say in 2 dimensions, and one would like to find feature sets that are useful for discriminating them. One of the features of the signature, which follows from the Stone-Weierstrass theorem, if you remember your undergraduate mathematics, is that linear functions of the signature are dense in all of the continuous functions on compact sets. So many problems can be solved with linear regression. One function problem here is this is about quantum computing, and it's a collaboration between Japan, Berkeley, and Oxford. A bottleneck in modern quantum computing is the ability to read out the results, which of course is quite important. And they discovered that signatures could be used to encode and then discriminate between the different outputs that you get for your readouts. And it makes a difference. It makes a substantial difference. And this has had two consequences. First is that the current version of the paper is with physical review letters, and so hopefully it will get accepted. But the other one is that actually we're collaborating with them to get all these calculations to happen at the nanosecond level on FPGA. And that's quite exciting too. But that all of that story I've shown you so far is more or less just classification, understanding functions on streams of data. Very important question, and not one that's actually very well tackled normally, precisely because people record data using streams, using time series, and they ignore the blow up of dimension that occurs if you sample highly. Um, so you do often achieve significantly better results. The next thing I want to talk about is a couple of examples which are based on can we learn from the past what's going to happen in the future? So this is a little bit more tricky. It's not so different to classification unless the future is complicated. But for example, Gonzalez and his colleagues in Scotland have tried to apply these techniques to understanding the life of a lithium-ion battery. So there you pump current in and take current out, and you create a signal, which is the path, and you use the feature set, which is the signature, and then you use linear regression on the feature set because you know it's adequate to try and find a good way of learning the life of a battery. And that paper is published in Applied Energy, which is a pretty good journal. This one is also really interesting. This is about 4 years old now. It was by Jinguo. Here, the challenge was actually some work that Jinguo did with Amazon. And there you have this enormously complicated middle bit where there are millions and millions of things going on, where lorries are moving things, aeroplanes are moving things, to get everything to the point where it can be distributed, the so-called middle mile. And the applied objective was to predict into the future what the demand was going to be in a month's time and so on, because you need to buy options for the transport and everything else. And if you look at the paper, they weren't doing very well. They weren't doing catastrophically, but the errors were in the 16, 20% range. Zinn took a considerable time and ingenuity and used the flexibility of the signatures to deal with streams to build a new model for forecasting, which just collapsed the errors more or less completely down to 1, 2, 3%. The, that's been running now steadily for 4 years, and Amazon estimates it so it saves them about 50 million US dollars a year. I guess it also probably saves some carbon, although American companies might not worry about that too much. But it's quite exciting. It'd be even more exciting if we found a way of getting some of that money back to Oxford, but that's beside the point. So the next question I want to talk about, which I think is a really important one, and is much more important than it looks, is if I give you a corpus of streams, which I think is normality, can we have effective methods for measuring the extent to which this stream belongs? Now, this is more novelty detection than outliers. we don't want the rarity of something to stop it indicating that something belongs. If it's in the corpus of normality, it belongs. And that's quite important because if you look at people moving around an airport and you want to flag that somebody does not belong, then you might find that some people have very strange routes, for example, the CEO, and you want to put those in and thereafter they belong. So the question is, does the stream belong? And you can apply this for malware detection. You can apply it, in fact, we did apply it for shipping data, but it's a very broad technology. But there is a very standard way we have developed now using Manor-Holobis distance and then nearest neighbor techniques that doesn't need any hyperparameters except the degree of the signature that can really be used to do this. It doesn't always work, but it works well in a lot of settings. And one of the things we've applied it to is actually an important question in astronomy. How you detect radio frequency interference. This is one of the key questions in modern radio astronomy because telescopes get more and more powerful. Human beings make more and more noise. And you starting your car can cause interference, which then gets mistaken for astronomically significant things. So what they would like to do, and they have software to do this, is to flag the intervals of time and the channels, because these are, many, many different frequencies all at the same time, that are actually subject to interference, because then they'll just strike them out from their analysis. And it's worth bearing in mind that these are big public ventures, and so SKA, which is the one we've been working with, cost about 1.9 billion euros to set up. So making them more efficient has a significant value. Well, anyway, using our methods of novelty detection, we were able to build a tool that identifies the unusual behavior. And where we differ from all the previous ones, apart from being significantly cleaner or more powerful, is that all the previous ones tended to say, well, noise looks like this, noise looks like that. Let's look for those things. Our approach turns that on its head. Our approach says, well, no, what we want is to understand what normality looks like. Let's give me a big data set as we can get of clean, useful data, can even be synthetic. And what we will do is we will notice in some relatively clever algorithmic way, but we will notice when it is not normal. We will notice the odd ones out relative to our normality. In doing that, you can build a very successful tool for detecting the noise that finds the noise that the others find, but finds it before and finds it after, but doesn't find anything else. So the truth is, it's just much more sensitive without introducing lots of false positives. That paper has been with the referees for 9 months or more, but hopefully at some point it will be accepted and will be good. Right, so how are we doing for time? Yeah, we have about 10, 15 minutes left. That's great. Because what I thought I would finish up with is to show you how this sort of approach can be used very widely in all sorts of different places. I'm not going to show you lots of them. I'm just going to show you another one. This time, the challenge, which is a collaboration and is being mainly operated by Ying Yi, is to recognize unauthenticated speech. So you may have read in the newspapers of how, well, first of all, you may have learnt by now how easy it is to generate speech. And much of the time, this is a really benign activity. And if we have time at the end or discussion, we can talk about lots of useful purposes of doing that. But for sure, modern generative models in data science can do a very good job. But criminals and bad guys have figured this out too. And there are lots of examples where people have been fooled by what they thought was their boss calling up or something similar, and have carried out transactions that have actually been disastrous. Um, there've also been people going the other way, people who've said things but would like to pretend it was a fake. So we're interested in whether or not we can build a tool which, if we focus on a particular individual and we collect have a private source of their data, are we able to distinguish between them calling up and some high quality clone or synthetic model of them calling up? That's the question we call the voice authentication question. So you have private samples, you don't really find them very expensive to collect. You build a reference out of them, and we would like to score the unauthenticated speech for its authenticity. And there's no doubt whatever that the modern methods are quite good, but we can, and this is what I want to explain, do quite a good job. The framework to do it isn't wonderful. Basically, we need about 2 minutes of speech from the incoming speech. And then we have enough information, really, with the current state of the art, to make a difference, to notice the difference. And the reason we can notice the difference is quite well defined. The first thing to understand, copy of the real thing. What is difficult, I mean, think about banknotes. We could just, photocopy a banknote more or less, and it'll be more or less identical. But actually, banknotes have serial numbers. And where we have difficulty is in having sufficient variety in the fakes. So actually, all of this work is about understanding the extent to which there is increasing novelty in contrast between our reference set and the data provided by the incoming unauthenticated speech. So actually what we do is the reverse of what you might imagine we do. We build a corpus of normality from our incoming speech. That's why we need 2 minutes of it. And then we test our reference sets, which are really only about 10 seconds each, for their innovation, the extent to which they are outliers from the unauthenticated incoming speech. And over the 10 seconds, we build a line going up, and each of these lines represents a different piece of our reference test speech over 10 seconds. You take the average and you get a mean amount of innovation between our reference speech and the corpus given by the incoming data. That sounds a bit complicated, but the reality is that if you were to try this many, many times with the true speaker, they're all concentrated in a relatively narrow band. The fake speech, however convincing, almost invariably is outside that band and does not match. Either you've introduced too much innovation that is not the innovation of the real speaker, or you've introduced too little. And just for fun, if we've got time, I think we've got time. Yeah. I'm going to play for you. I hope it works across the across the internet. Um, the real voice.
We are sitting at a table and we are writing this up on paper made thousands of years ago. Like we can see the golden one, only one lock of gold on the pillow of this is our home. We came upon it today at sunrise. We are sitting at a table and we are writing this upon paper made thousands of years ago. The light is dim, and we cannot see the golden one, only one lock of gold on the pillow of an ancient bed. This is our home. We came upon it today at sunrise. For many days, we had been crossing a chain of mountains. The forest rose among cliffs, and whenever we walked out upon a barren stretch of rock, we saw great peaks before us in the west. We are sitting at a table, and we are
No,
writing
no.
this on paper made.
Okay. Well, I think you'll agree that probably you can tell the difference, but actually that it's quite an important question, and it's easy to understand how some poor administrator somehow did not get it right. Um, I think it's quite an important and interesting question. I want to finish up just by saying that none of this happens without computing. And actually, as we develop our technologies, the computing associated with this is quite sophisticated. I mentioned non-commutative groups, but actually, there are free algebras, free tensor algebras, there are cotensor algebras, there are shuffle products, there are adjoints of tensor multiplication, a huge number of quite complicated operations and techniques needed to put this all into practice. Um, We have many, many years ago, probably about 2006, I wrote a very simple package, which basically computes signatures and log signatures. Log signatures are complicated because they're Lie elements and because there's no canonical basis for Lie elements. And so you have to figure out how to find a basis. Fortunately, Bourbaki wrote lots about different bases for the free Lie elements, and you can implement all that. And it seems that people still find this valuable because if you look at PyPy, it's downloaded 25,000 times a month. But actually, it's not sufficient for the current day. And the current kernels and things really need far more sophisticated math. And we have been developing a new package, which I encourage you to check out, called RoughPy. At the moment, it's only based on the CPU and it doesn't have differentiability. Two obvious downsides, but those are simply amount of resource we have to try and make something really useful. I'm pleased to say that we recently just got a new grant, and that grant has a large component which involves developing these tools for the GPU. Um, you'll also find on our website, actually, www.datasig.ac.uk, a number of it works examples that you can look at to see the different sorts of things you can do. We're also trying to uh, commercialize some of this. I don't think there's any doubt that there are lots of different directions. We're interested in um, doing some drug discovery, but also my colleague Weishan Yang is doing some great stuff in image restoration. That was the original image taken by Ling Yi in her garden, and that's the improved version. And the interesting thing about these examples is they don't have a ground truth. Again, they're not machine learning. You can use machine learning afterwards to make them faster and better, but this is the first step. I think that's about all I really want to say. I don't want to talk anymore. I'm happy to answer some questions, and I hope you found it interesting. Thank you very much.
Thank you, Terry. We've got a good amount of time for questions. So anyone who'd like to ask a question, either post it in the chat or the Q&A or raise your hand and we can unmute you and allow you to ask a question. So to kick off, Terry, any of these methods, because they're very flexible, they do allow lots of different things, you generally would need quite a lot of data to work with. Do you see these as having uses primarily in those data-rich contexts, or do they play well with dimension reduction in low-dimensional contexts as well? Do you have anything to say about this?
I think the opposite, because they're not clumsy, they probably can make do with as little data as you can manage if they're well structured. I think a good example of that, although I didn't talk about it, was the paper I put on one of the early slides for the mental health, where we explained how simply self-recorded mood data over a period of time, mood is a seven-dimensional vector, essentially, anger and disgust and things like that. But just understanding the order in which they happen, the second order level, we were able to quite comfortably distinguish between the three groups in the experiment, who were people who had a diagnosis of a bipolar disorder, people who had a diagnosis of a borderline personality disorder, and people who had a diagnosis of normality. And we were able to quite easily discriminate between them. But yet to understand that from a data set size, we did it with a 50-dimensional feature. And we did it with about, by the time we cut everything up into pieces, 2,000 data points. And with no machine learning, just regression, right? I think in general, if it is about order of events, if that actually matters, then that is so dominant, actually, that we will do quite a lot better than anything that is careless with that data.
Thank you.
That's
There's a
why we
question.
won on the sepsis.
Maybe I will follow up, Terry, and Sam's question then, because I wanted to go to the very beginning of your talk, where you've said, that the context can matter, but this is sort of, these methods don't really look at the context, and maybe this is related to you didn't really talk about the fact that whether how the methods perform under reparameterization of your data. And what's invariant under parameterization, what is not. So I'm just wondering whether you might comment on the representation of the data and the issues with parameterization or lack thereof, and then how would you include context in this?
Maybe I'll answer the second one first. I mean, a calculator doesn't use context, but the questions you ask do. Right? So I think it's automatic that if you ask intelligent questions, you're going to include context. And I think we were including context in our fake speech and all the rest of it. But the question about reparameterization, I think, is a more technical question. Okay? If you have a stream of data and it's multimodal, you often do not care with great accuracy when things happen. You do care quite often what order they happen. You do care that your building falls down because of an earthquake, but you don't actually care whether it fell down at 11:03 or 11:05. Actually, this is quite a challenging point, because often when we solve PDEs, we do it by doing a sequence of timeframes and saying where we are at the different times. That actually carries a very high penalty in terms of expense if you really think it through. So the advantage of using the signature, for example, it was used very much in a very small data set in detecting Alzheimer using weights of various components in the brain some while ago, is that if I have a sample with 5 data points or 7 data points, then the signature is going to be broadly dependent on the shape of that curve, or the curve that's sort of approximated by those points, and doesn't really care whether you use 5 or 7 data points to achieve it. So you're able to look at your stream of data and make assertions about it without understanding or needing to understand the data sampling rate only really whether the data sampling rate was adequate to describe the data. This already is a big improvement compared with most things that tend to say, I've got to make a 5-dimensional variable, and so I've got to have the same number of sample points. And then you start doing all sorts of horrendous things like filling in the gaps and, which actually have very little meaning to them, except that your methodology doesn't know how to handle them. Signatures are very convenient from this perspective. Where they go wrong, and they do go wrong, and they're not a panacea, is that they're extraordinarily useful for describing complex oscillatory data over relatively short, and we can discuss what that means, time intervals. They're really the wrong idea if you want to describe a series over a long time interval. Basically, they should be used in intervals, just like the classical time series. But the point is that the objects you put in the intervals should be richer than the value at each end. And that time series really comes from, the time scale really comes from the context, again, that you care about. So when I speak, the truth is that I'm sending out lots of very high frequency relative to my speech vibrations, and people are interpreting them. But the speed at which we're interpreting is maybe 1/10 of a second, or even more. I don't know how many words in a minute, but I mean, in a second, but they're not very many. And we don't actually care about the response in shorter periods than that. So the signature is going to work really well at summarizing the oscillations within a consonant or within a phoneme. It's going to do really, really badly if you try and describe an hour speech with one signature, and you're going to need exponentially many terms, because there are exponentially many possibilities for what was actually said during that period, and there's no escape. So I don't know if that answers your question, but
Now I see Krista has her hand up, but before then we have 2 questions that have come up in the Q&A. So one from Kami Ayati, what is your idea for the future of cloning streamed data?
do you mean cloning or generating? Cloning seems easy.
In what
I think
sense?
maybe, I mean, if you mean do I think of the future of generating speech, I think it's here to stay. We'll use it. Even I've used it. It's really, really useful to be able to type a lecture. If I had a choice, I would put this lecture, I would have a synthetic version of me giving this lecture, because I could choose my words carefully. I could make certain I didn't misstate anything. And what's more, I could run it again and get my money's worth out of me. But I think it's definitely here to stay. There's so many practical real world uses in training videos and things like that. I also illustrated that there are bad guys who can use it bad ways. If you're talking about generating data in general, cloning in that sense, cloning similar things, then of course it's incredibly important too. And signatures can help that by understanding whether it's accurate and locally distributed correctly, but lots of other things are involved as well. I mean, diffusion models are fantastically important, fantastically successful. None of this stuff is going to go away.
On that note, I should say that all the SIAM talks, including this series, are posted on YouTube afterwards. If people do want to get their money's worth out of Terry's talk, it will be up in the near future. Next question, how do these approaches perform in a heteroscedastic noise setting?
That I think I never know what heteroscedastic means, but I can guess. But that to me is exactly the context of the Amazon middle mile. They perform extraordinarily well. The whole point is that they give a rational way of explaining and learning complex nonlinear interactions. And those nonlinear interactions can discuss and involve order of events on different channels.
Krista, please.
Hello, Terry. Thanks a lot for the great talk and the fascinating results. I just wanted to ask, maybe coming back also to Jan's question. So, what would you say? What are the distinctive advantages of the signature as a feature map with respect to other feature maps on path space? So is it the linearity? Is it the reparameterization invariance? Is it the fact that it works on small data sets? So what would your answer to that? And also maybe compared to I don't know, Fourier basis or wavelet basis or something like that.
Okay. Okay. Well, let's start with the Fourier basis first, because the Fourier basis makes it clear what goes wrong. Right? The Fourier basis suffers from the same problem as time series, that actually it treats each channel separately. And the only way you can figure out the interaction between the channels is by developing each channel accurately enough that you can then go and look at them classically and see what's happening. I think one should not underestimate that the parameterization invariance is actually something necessary to understanding most multimodal data. It's not an optional thing, right? But the signature is not the only tool that can deal with that. In fact, anything that involves solving a differential equation, for example, an RNN, will achieve that, not necessarily universally, but will achieve it. I think the signature is obviously, and I alluded to that over long intervals, the wrong thing. It's not the right thing always. It's not a panacea. I think it's a mathematical object. I think in a way the question is a bit like saying, well, what is the point of the representation of a real number as an infinite expansion? You know, in some everyday point, we're never going to use it, but it still has considerable conceptual advantage. And a lot of the questions, I think, are actually going to be directed over the next few years as people understand the connection between these things and large language models, of actually how you choose the bits of the signature that might be important to you, right? But even there, it is not true, because I explained to you that it's a representation of the exponential function. Put an I in there, and you switch between Laplace transform and Fourier transform, but in this non-commutative correct sense, rather than the bad sense that we were talking about before. And they give different representations. If you have the whole series, they give the same representation, but if you only have a partial series, they tell you different things. So with the I there, it's telling you about the texture of the stream. Without the I, it's telling you about the structure of what it does. And it clearly telling you different things. So most probably a really good model will do both. A little bit of one representation, a little bit of another. The great thing is this is all math. And there's a lot to think about, and I'm pretty confident over 20, 50 years, people will have thought about much of it, and there will be relatively clean answers. But the signature is not the only representation. And indeed, you can do a random image of the signature, and that would be pretty much reservoir computing.
Yes. No, but for instance, you mentioned recurrent neural networks. So, with respect to, I mean, do you think that the applications that you used here, that they could be similarly well achieved with recurrent neural networks, for instance?
No, I think they could be an R achieved by neural differential equations. The point about an RNN is it locks in time steps. An RNN locks in the number of steps in your interval, which a neural differential equation does not.
Okay. So,
Right,
but
and
the
therefore
continuous time limit
the partitioning is not data dependent. The great thing about using a neural differential equation is that your numerical analysis to compute the differential equation can be data dependent. And providing it's done properly, there is no derivative there. It's not something you need to learn. You just solve the differential equation adequately. This is a big plus, because it means that your architecture adapts to your data.
Yeah. Okay. Thanks a lot.
Thank you for some great questions, and thank you for having me.